I'm sure you won't be surprised to hear this, but there have been a million amazing scientific discoveries in the last 200 years. Life for human beings on the planet has changed so dramatically from having to light your house with candles to entire electrified cities so that when you're flying over a city in an airplane, it looks like a big giant circuit board. All right? We've gone from having no antibiotics, meaning if you have some sort of, bronchitis or, other disease, there's many, many bacterial illnesses. You just had to wait until hopefully it was over, or you don't and you just pass away, right? Transportation, airplanes, space travel, you name it. There have been so many discoveries in the last 200 years. And I'm going to go out on a limb and say that none of them are as important as the discovery that I'm going to share with you in this video. Now, why is this discovery so important? Well, first I should probably say what the discovery is. The discovery is something called electromagnetic induction, and it was discovered by someone named Michael Faraday, who was a surprising genius even though he never went to college. One of the greatest experimentalists in the history of science, and he never went to college. And his name is in every physics textbook that you can find now. So he discovered that if you change the magnetic flux through a loop of wire, okay, so if I change the amount of magnetic field that's moving through this loop of wire, right, I suddenly have a current in that wire. From nothing, I have a current. Now, you may be like, how is that cool of a discovery? Well, it turns out every form of power that we have, every power plant, just take a windmill, right? What is a windmill doing? A windmill, wind blows through it, right? And the turbines start turning. That turning turbine is actually just to turn a magnet to change the flux through a coil of wire so that that coil of wire then has a current that moves through it and sends electricity off into your home, okay? Now, what about a hydroelectric dam? Well, the water flows onto, again, turbines, right, that turn a magnet, that change the magnetic flux inside of a coil, that induces a current, and that current goes to your house and allows you to power everything in your home. What about nuclear power? Well, nuclear power plants use nuclear reactions to boil water, to create steam, to go through a turbine, to turn that turbine, to turn a magnet, to induce a current in a coil that then sends electricity off to your house. Every single major type of power plant in the world right now, except for solar actually harnesses the power from the sun, but all the mechanical power plants, their job is simply to turn a magnet, to change a flux, to induce a current in a coil to send electricity off to your house. All right? Now, I ask you, how valuable would any of those other discoveries be? Vaccines, antibiotics, space travel, flight, if you did not have the power to power the factories that actually make those things, right? The whole reason why we're actually able to do all this stuff and enjoy life the way that we do is because we've found ways to harness electric power, and that primary way of harnessing electric power is through this thing called electromagnetic induction, which we're learning about this week, and which is why I think it is probably the most important discovery in the last 200 years, and you get to learn about it this week. All right, now with that extremely large build-up, let's go to the quote of the week. It's from someone named Byron Katie, an author, who says, "As long as you think that the cause of your problem is out there, as long as you think that anyone or anything else is responsible for your suffering, the situation is hopeless. It means that you are forever in the role of the victim and that you're suffering in what could be paradise." Now, this doesn't mean that bad things don't happen to people. And it doesn't mean that there's not actual suffering that happens when we lose somebody or when we get sick, right? But I think what Byron Katie is saying here is that the story that we tell ourselves, the thinking that comes all along with it, right? And how we can negatively respond to these things, that is really where the suffering lies. That's where, I can accept being sick, right? I can even accept having cancer. But if I have this story that I keep playing in my head and I live the last days of my life with this story of, I am a victim, poor me that this is happening to me, why me? I don't deserve this. If I am focusing on all those thoughts, how much more suffering than if I just live the rest of my life doing exactly what I should be doing and what I want to be doing. You notice maybe that a lot of the quotes that I pick for this course really revolve around this idea of how much does our own thinking and the stories that we tell ourselves affect our ability to enjoy life and to be successful, happy people. And I think there's a lot to that. I think this little voice in the head can be our own worst enemy sometimes. And that living a good life means being able to be aware enough to recognize when the voice is not telling us a story that's serving us and being able to let it go. All right, so with that said, I will move on to the why do we care question. And this involves the genius of a crocodile. So it's not just humans that use the power of electromagnetic induction, but it's actually animal life as well, including the crocodile. Crocodiles seem to have the ability to detect the direction of the Earth's magnetic field. Pretty cool. Inside the creature's brain, there are loops of neurons about 1 micron in radius that pick up induced currents when the magnetic flux changes. In other words, if the crocodile turns its head, that head is moving in the Earth's magnetic field. So in other words, there's going to be a change in magnetic flux through certain neuron loops inside that crocodile's brain. Okay? Imagine the crocodile is facing north and then rotates its head 90 degrees until it's facing east in a time interval of 2.7 seconds. What is the average EMF induced around this loop of neurons? By the end of this chapter, you will be able to calculate that. Pretty cool, right? All right. I want to move on to just a brief introduction of this fellow Michael Faraday that I mentioned. And I'll just go ahead and read this. Sometimes in life, a human being rises to prominence through passion and self-education alone. This is still possible, right? As recently as Steve Jobs, first of all, I just want to say I believe strongly in a college education. But Steve Jobs had an idea, had some passion, and built the Apple empire without a college education. And I think it's just a testament to it's not just school that matters, right? It is also what you're bringing to the table in terms of your own passions and in terms of your own ingenuity and making whatever you do in life meaningful to you. Okay, so Michael Faraday was a physicist without a high school education, and yet he is the reason that you flick a switch on and electricity lights up your home. Okay, so hopefully it's a semi-inspiring story about how even people in lower classes with almost no education can find a way simply by discovering what they really care about, clarifying that for themselves, and then driving full force ahead with it. Okay, anyways, what did Faraday see that changed the world? Well, here's the thing. He noticed that if you had a little loop, right, as you can see in this picture, if you had a little loop and you took this magnet, okay, and you put it in and out of that loop, and that loop was connected to an ammeter. Remember, ammeter measures current, right? And then let's suppose that you took that magnet and you moved it in and out of that loop, as you can see from this picture right now. You take this little magnet and you move it in and out of the loop. He noticed that the little needle on the ammeter would fluctuate, right? It would do this, and then it would do this way, this way, this way, this way, this way. And he was like, whoa, normally it would take a battery to do this. I have no battery in this little loop. And yet, just by moving a magnetic field through it, I'm seeing a little current go, ju, 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 right? Okay, so he's like, this is pretty magical, right? Okay, so what else did Faraday see? Well, he saw that it doesn't even necessarily need to be a magnet. He took another current loop, right, but this one with a battery, and he closed the switch so that the current started going through the current loop, right? As you remember from last chapter, if the current is going through the loop, it's going to create a magnetic field all of a sudden. So he found out that if you close the switch, the little needle moves again. Little needle moves again, okay, in another loop connected next to it. So basically, what would you conclude if you were Faraday and you were seeing this? Well, both a magnet and a current-carrying wire, as in the second example, both of those things have a magnetic field, right? But he discovered it wasn't just having a magnetic field that was enough. The magnetic field had to change, right? So in the second example, there was no moving of the current dial until the circuit was closed, the switch was closed in the other loop, the one that was creating the magnetic field. Okay? So in other words, the magnetic field went from 0 to something, and then you close the switch and it goes away again, and then the little dial would move again. So he discovered that it was only when the magnetic field that was moving through the loop changed, and then he would get a little bit of a reading on that dial, okay? And so from this, he created something called Faraday's Law, all right? And before we totally explain the full beauty of Faraday's Law, I want to remind you guys of this whole concept of magnetic flux. We talked about it last week, so I'm just going to review it really quick. Magnetic flux is just this whole question of how much magnetic field is penetrating a certain surface. Okay, so let's say this is a conductive loop right here, right? And it has a certain area, A. Okay, so that would mean that the flux moving through this wire is B times A, right? But we also talked about, well, what if the wire is at an angle, and so there's this area vector that's normal to the surface of the loop, okay? But the B field is still going this way, right? Well, in that case, we found out that the flux was equal to B A cosine theta, right? The flux is still B cosine theta here, right? But the angle between the area vector and the B field is 0, right? So we have BA cosine of 0 is just BA, right? But in general, right, there might be some angle here, right? So let's say it's 30 degrees, then this would be, the magnetic flux would be equal to BA times cosine of 30 degrees. Since this was a circle, the area would just be equal to pi r squared, right? And the B field is, whatever they give you for the B field, right? So this concept, I promised you last week, would be very, very important for this week. And the reason is because it turns out that what Faraday noticed is that it's really the change in flux that's creating this current, okay? Right? In fact, what he found is that, and this is Faraday's Law, what he found is that there is an induced EMF, and this little cursive E here means EMF, means electromotive force, same thing as a voltage, right? This is just a fancy term for voltage, because not all EMFs are the result of batteries. As you can see, sometimes there's an EMF that's the result of a changing flux. So he found out that the induced EMF in a circuit is equal to the change in flux with respect to time. Okay? That's all. That's all. He found out that if you just change the flux, right, over a certain time period, you can get an EMF acting like a battery from nothing. So in other words, I don't even have to put a battery in a circuit. All I have to do is change B, A, or theta, and I have an induced current. Okay? Why it's called induced, we'll explain a little bit later. But this was revolutionary, and as soon as we realized we could do this, we started to realize, wow, there are so many ways that we could harness the power of electricity beyond just simple batteries, and we went crazy with it, and now we have this electric circuit board of a life that we have right now. So I have a couple more slides here on magnetic flux as a review from last week. I encourage you to take a look at them, remind yourself of how flux works. If you don't remember, there is a flux problem, which was actually in the last video as well. So you can check that and do that again if you'd like. But when we get back to the next video, we're going to talk about the next step to fully understanding Faraday's law, which is something called Lenz's law, which is the rule of what are the rules for how the induced current is created when I change the magnetic field or I change the flux through some loop. All right, I'll see you there.